Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the problems on springs. In the previous session, we have studied there are various types of the springs. One is laminated or leaf spring, another one is coiled spring. Helical springs. Again, helical spring is classified into subcategorized into two types. One is open coil helical spring, another one is closed coil helical spring. So we derived expression of closed coil helical spring by considering the axial load is acting on the spring. We expressed what is the shear stress, what is the deflection and the stiffness expressions we have derived in the previous sessions. Now in this session we are going to solve the problems by using those expressions. How to use those expressions in solving the problems. So here a closely coiled helical spring is to carry a load of 500 newtons. Its mean coil diameter, capital D, equal to is to be 10 times the diameter of the wire. Now here wire diameter, and calculate these parameters, these diameters, that means capital D and small d. If the maximum shear stress in the material of the spring is to be, that is 80 Newton per square millimeter. Okay, that is 80 Newton per square millimeter. Tau equal to 80 Newton per square millimeter. Now here the capital D and the small d, the mean diameter and the diameter of the wire. The capital D equal to 10 times the small d. How to find out the capital D and the small d? And here there is the shear stress value is given. Now here, based the relation, the formula expressed in relation to capital D, small d and the tau. The equation is that, the relation is that is tau equal to 16 times WR by pi d cube. Here tau equal to what is the W here? The load acting axially, and capital R, that is the mean radius, and pi d is the diameter of the wire. Now if you substitute here, considering tau equal to 16 times WR, here R equal to D by 2, that is pi d cube. Now that is 8 times WD by 2 pi d cube. We know that capital D equal to 10 times small d. In that here 8W times 10D by 2 times pi d cube. Yeah, that is pi d cube. What is pi d cube? Again d cube, here d square. Now here 18W by pi d square. That is the shear stress. If you substitute W value, the W value is 500 newtons, and the tau, that is 80, and D can be calculated. The calculated D here, it is 1.2, that is 12.6 millimeters. Now this we know the small d, that is the diameter of the wire, that is 12.6 millimeters, and we have to find out D equal to, that is 10 times small d, that is 10 times 12.6, that is 126 millimeter. The mean diameter of the wire is 126, or in terms of centimeters, 12.6 centimeter. Okay, and in terms of that here, that is 10 times 12.6, that is 12.6 millimeter for the diameter of the wire, that is 1.26 millimeters. The 1.26 millimeter means it's very thin wire, and the diameter and the mean diameter is the 12.6 centimeters. So the spring here, the helical, closely coiled helical spring, is the thin 1.26 and the larger. So by this we can understand that this type of springs are useful for in the case of sofa sets inside, and the beds are useful for the more cushioning effect. That's what we can understand. Based on the geometry and based on the values of the mean diameter and the diameter of the wire. Now one more thing, very interesting thing, here it is how this formula is obtained. Instead of remembering, that is a tau T equal to 16 times WR by pi d cube. That is tau equal to 16 times WR by pi d cube. What is WR here? That is the torque. That means 16 times T by pi d cube. Tau equal to, now torque T equal to pi by 16 times tau d cube. This is the torque formula, the relationship with the torque. This is the T equal to pi by 16 tau d cube. This formula is derived, this equation is derived from the pure torsion equation. That is tau by R equal to T by J equal to G theta by L. From this relationship, we got this equation, that is tau equal T equal to pi by 16 times tau d cube. So here, from this formula, we got it the shear stress. Alright, so that the pure torsion equation is highly important in order to derive the expressions of the shear of closely coiled helical springs, the shear stress, the deflection, and the stiffness. Now, next problem. In the next problem, if we consider the model number 2, in this problem here, a closely coiled helical spring, the same data which was solved before, is to carry a load of 500 newtons. Its mean diameter is 10 times that of the wire diameter, capital D equal to 10 times small d. Now, and calculate these diameters if the maximum shear stress in the material of the spring is, that is 80 Newton per square millimeter. If the stiffness of the spring is 20 newtons per millimeter, and the modulus of rigidity C value is 8.6 into 10 power 4 Newton per square millimeter. We have to find out the number of coils in the closely coiled helical spring. What is N equal to? So from this capital D and small d, from this first part we have to follow, that is a tau equal to 16 WR by pi d cube. Tau equal to 16 times WR by pi d cube. From this relation, if you substitute capital R equal to D by 2 and substitute the relation of capital D equal to 10 times small d and calculate the values, we already calculated the value. The values, calculated values are capital D, that is 126 millimeter, small d 12.6 millimeter. So here, that is capital R equal to small d by 2, that is capital R, that is 126 by 2, that is 63 millimeter. And we have to find out the number of coils in the spring. What is the number of coils are there? The number of coils in the spring. But one thing, the data is given here, input data, that is stiffness. The stiffness, that is K equal to 20 newtons per millimeter, or S equal to, in our formula here, the stiffness S, K or small letter S. So S equal to 20 Newton per square millimeter. We have the formula, we express the expression we have between the stiffness and deflection. That is the stiffness S equal to load per deflection. Load per deflection. What is the load here? The load is here, that is 500 newtons axial load, deflection. The deflection has to be found. And where is the S here? What is the S? Stiffness value. The stiffness value is 20. Now from that, the deflection equal to 25 millimeters. And from the deflection, we know the deflection formula in terms of number of coils in the spring. Deflection delta equal to 64 WR cube N by GD power 4 or CD power 4. Delta equal to 64 WR cube N by GD power 4. From that, we know R value and D values, we know G value, that is modulus of rigidity, or C value, and delta we calculated. Other things, if we substitute here delta, the value of the delta is 25 millimeters, 64 times axial load, that is 500 newtons, that is R value 63, that is mean radius of the coil, that is 63 cubic N by G, that is the C, modulus of rigidity value 8.4 times 10 power 4. What is the D value? Diameter of the wire is, the diameter of the wire is 12.6 millimeters, that is 1.26 centimeter, that is 12.6 millimeters. Now, by substituting all the values, the unknown is the n. The n value is calculated as 6.6. That is the number of coils in terms of 6 times and again 60%. That is the 6.6. So we can consider this closer to the 7. That's why the number of coils of the spring n equal to 7. So the formulas we use here, there are two formulas are used in order for calculating the number of coils. The number of coils calculated in this formula number 1, that is T equal to, that is pi by 16 times tau d cube, that is nothing but tau equal to 16 times WR by pi d cube. This is the formula, this first formula in order to for calculating capital, that is the mean diameter and the diameter of the wire. After using this formula, the next formula we use here, delta equal to 64 times WR cube n by GD power 4. So here from this diameter of the wire, mean diameter of the coil here, that is capital D, that is capital D equal to 2 times R. From this R value we got here. And axial load W, and N is the number of coils which is going to be calculated. And small d is the diameter of the wire. Capital G is the modulus of rigidity. 64 times WR cube N by GD power 4. That is the delta. So deflection, how we calculated deflection? Deflection, we know the deflection by using the stiffness parameter, stiffness S equal to load per deflection. From this, deflection is calculated. The deflection we know 64 WR cube and GD, but N, which is the unknown. The N is calculated here, the number of coils. So how many in detail, there are three formulas are used. Three formula are used. The first formula is a tau equal to 16 times WR by pi d cube. The second one is the stiffness equal to load per deflection. And the third one is delta equal to 64 times WR cube N by GD power 4. This WR, where R is the mean radius of the coil, and D, small d is the diameter of the wire, where G is the modulus of rigidity, or another name is called shear modulus, and W is the axial load, and where delta is the deflection. Now, what are the units for this? The units for delta is that the deflection unit is millimeter. What is the unit for axial load? That is newtons. Unit for mean radius, capital R, that is in millimeter. And what is this G? Modulus of shear modulus. The shear modulus, units per shear modulus is Newton per square millimeter. And the diameter of the wire, D is in millimeters. And N is the number of coils, no unit, is the number of coils, number. From this, the number of coils obtained in this formula, in this problem, is 7 coils. That means here the 7 coils, 1, 2, 3, 4, 5, 6, 7. Now here 7 coils, exactly here it is done. When you round figure here, the 7 coils, the value here, it is subjected to, what is the axial load? The axial load is subjected to 500 newtons. 500 newtons. Alright, the mean diameter here it is 63 millimeter. It is the 63 millimeters, and the small d is the diameter. The small d diameter is 12.6 millimeters. So the input parameters are here: mean diameter of the coil, or mean coil diameter, and diameter of the wire, and the shear stress, axial load, modulus of elasticity, the value of modulus of elasticity, and stiffness. The output parameters here it is only the number of coils. How to calculate the number of coils? Number of coils in the closely coiled helical spring. Now coming to next problem, based on the formulas we use, here, we expressed in previous session, that is the shear stress expression, deflection expression, and stiffness expression. A closely coiled helical spring of round steel wire, that is 10 millimeters. Round steel wire is 10 millimeters in diameter, having how many number of turns? Then n equal to 10 and d equal to 10, with a mean diameter of 12 centimeters, that is 120 millimeters, that is a capital D, to an axial load W, that is 200 newtons. Determine number 1. First objective is deflection of the spring. The second objective is maximum shear stress in the wire. And the third objective is the stiffness of the spring. Take the property of the material, that is the modulus of elasticity, C, capital C equal to 8 times 10 power 4 Newton per square millimeter. So by using these parameters, these input parameters, we have to derive or we have to calculate 3 objectives: deflection of the spring, maximum shear stress in the wire, and the stiffness of the spring. So we know the deflection of the spring. The deflection of the spring equal to 64 times W R cube N by C D power 4. Okay. And the maximum shear stress tau equal to, what is this tau equal to? That is 16 WR by pi d cube. That is the second objective formula, and this for first objective. And the stiffness comes, the third objective formula, the expression is that stiffness S equal to load per deflection. By using these 3 relations, we can calculate the deflection of the spring, the maximum shear stress, and the stiffness of the spring, that is W by delta. Okay, let us begin. If you substitute, what is the 64 times W axial load 200 newtons, R equal to D by 2, that is 60 millimeters. N is the number of coils, N equal to 10. C, the modulus of elasticity, modulus of rigidity, that is the shear modulus, that is 8 times 10 power 4, where D is the wire diameter, that is 10 millimeter. After substitution, directly we get it delta deflection. And in the case of second objective, tau equal to 16 times W, that is the axial load 200 newtons, R, that is the 16, and pi times D, diameter of the wire 10 cube. Now stiffness S equal to W by delta. S equal, what is the low axial load? 200 newtons by delta, the deflection, which is calculated in as objective 1. Substitute back in the objective 3, formula, then you get the stiffness. Let us go for first equation. 64 times W R cube N by C D power 4. 64 times W 200 times R is 60, substitute R cube cubic R, the N 10 by C 8 times 10 power 4 D. D value diameter of the wire, that is 10 millimeter 10 power 4. The deflection is under the axial load of 200 newtons. For the geometry, the cross section of that is 10 millimeter wire and the mean diameter 60. The obtained deflection is that 34.5 millimeters. Now what is the shear stress? The shear stress tau equal to 16 times WR by pi d cube. 16 times W 200, what is the R? 16 by pi d 10 cube. That is 61.1 Newton per square millimeter. Next, stiffness of the spring. The stiffness of the spring is S equal to W by delta, load per deflection. What is the load, axial load here? That is 200 newtons by delta, here it is 34.5. That is a delta is obtained value. After substitution in this, we'll get 5.8 Newton per millimeter. Okay. So these are the 3 objectives derived in this problem, which was asked as an objectives. By using the input parameters are number of turns, mean diameter, axial load, and modulus of rigidity value. And finally, wire diameter also mentioned here. The next problem here is we are going to solve here. We are going to calculate the deflection and also stiffness. And third objective is the frequency of the free vibration of a mass hanging from it. Okay, let us read. A closed coil helical spring This is the closed coil helical spring of 10 millimeters mean diameter, 10 centimeters mean diameter, that is 100 millimeter, capital D equal to 100 millimeters, is made up of 1 centimeter diameter rod, 1 centimeter, that is 10 millimeters D, and has 20 turns. Here this value indicates N value, N equal to 20 turns. The spring carries an axial load of 200 newtons. The spring carries an axial load of 200 newtons, W. Determine the shearing stress as tau value. Next, the diffraction, take the values of modulus of rigidity, that's C equal to 8.4 times 10 power 4. Determine the deflection when carrying this load. What is the deflection? Also calculate the stiffness and also the frequency. The frequency is the F, as the frequency, F equal to. These are the 4 objectives ought to be. Yes, let us go for shear stress. The value of, what is the formula for shear stress formula? Shear stress formula T tau equal to 16 times WR by pi d cube. We know the mean diameter, the mean radius comes, W axial load is 200 newtons, pi times the small d diameter of the wire, that is 10 millimeter. Directly the shear stress will be obtained. And what is the second objective? The second objective is delta, that term deflection. Delta deflection equal to 64 times W R cube N by C D power 4. 64 times W here known, R also known, R is known, N number of coils, 20, C modulus of elasticity, the modulus of rigidity value, that is the shear modulus value. Where is the D here? Diameter of the wire, that is 10 millimeters. C for shear modulus. Substitute here, then the second objective can be calculated. And the third objective is the stiffness. The stiffness S equal to load per deflection. Then we know the axial load of that is 200 newtons by deflection value, which will be calculated here as objective 2. Substitute here, then the objective 3 can be calculated, can be achieved. And finally, F, the frequency of the vibration. The frequencies of vibration in terms of delta. We know that frequency of the vibration in terms of the delta, that the fourth objective, F equal to 1 by 2 by times under square root of G by delta. What is the G value? 9.81 meters per second square, convert into millimeters. Now delta is in millimeters. Deflection should be calculated here in delta as objective 2. Now let us begin. Equation 16, that is the shear stress, maximum shear stress, 16 times WR by pi d cube, 16 times W 200, R 50 by pi d, d is the 10 cube, that is 50.93 Newton per square millimeter. The second objective, deflection of the spring, delta equal to 64 times W R cube N by C D power 4. Yeah, substitute here the known value, 64 times W 200, R 50 cube by N is 20 by C 8.4 into 10 power 4, D 10 power 4, G is the 10. That's 38.095 millimeter can be observed here. Okay, and finally the stiffness of the spring. The stiffness, yeah, last but one here. The stiffness of the spring is the first objective, the second, and the third objective is the stiffness of the spring. The stiffness of the spring equal to load on the spring by deflection of the spring. What is the load? 200 newtons. The deflection is achieved here. That is 38.095. That is 5.25 Newton per square millimeter. Newton per millimeter. And the fourth objective is frequency of the spring. The frequency of vibration. The frequency of the vibration, we know the delta value, that is 38.095 millimeters. Convert into centimeter or meters according to the requirement here, then 3.8096 centimeters. So the frequency here they convert here, this 981 converted into in terms of centimeters, centimeter per second square, that is 981 by 3.8096 96. Then the 1 by 2 by times and the square root of g by delta. That is 2.5 cycles per second. F equal to 2.55 cycles per second. Objective 1, that is the shear stress, maximum shear stress. Objective 2, deflection. Objective 3, stiffness. Objective 4, frequency of free vibration. Yes, 4 objectives are achieved by using. Yeah, so simple if we remember the expressions. This is what. What is the expression 1? Shear stress 16 times WR by pi d cube. What is the expression of the deflection? 64 times WR cube N by CD power 4. The stiffness of the spring, that is in terms of load and deflection, that is stiffness S equal to load per deflection W by delta. And finally, the frequency of the free vibration, that equal to F equal to 1 by 2 pi times and the square root of G by delta. These expressions, by practicing, you can remember easily, and direct substitution. And according to the requirement, we have to apply the data. Okay, suppose they have given the mean diameter. We need here, suppose if we consider the shear stress expression, in the expression of the shear stress, where capital R is mean radius coil, okay, not mean diameter, the mean radius of the coil. That's a capital R. Suppose in the problem, it is given here, it is as the mean coil diameter. We have to convert the diameter into the radius by substituting, by dividing by 2 of the mean coil diameter. That is d by 2 equal to mean coil radius. In that manner, we have the data and these expressions in our mind. If you remember thoroughly, we can apply the data where it will be fit for. That's what we have to crack the problems here. So, and the concepts, those expressions, how those expressions are derived. We have a practice thoroughly, then we can apply those expressions in solving the problems. Now, the next problem here it is a closely coiled helical spring of mean diameter, a closely coiled helical spring of mean diameter, that is 20 centimeters, that's capital D equal to 200 millimeters, made of 3 centimeters diameter rod. What is the 3 centimeters? That is the diameter of the wire, small d, equal to 30 millimeters, and that is called small d. And the number of turns 16, n equal to 16 turns. A weight of 3 kilonewtons is dropped on this spring. 3 kilonewtons weight dropped weight. Okay, that is 3000 newtons. Find the height by which the weight should be dropped before striking the spring, so that the spring may be compressed by 18 centimeters. There is a deflection, delta equal to 180 millimeters. Now, and the property of the material, that is the shear modulus value is 8 times 10 power 4 Newton per square millimeter. 8 times 10 power 4 Newton per square millimeter. Now, what to be found? We have to find out objective 1, that is a height through which, find the height by which the weight should be dropped before striking the spring, so that the spring may be compressed by 18 centimeters. The spring got compressed. The expression is the most, the practical, the field application problem. What is the height, dropped height of the weight, such a way that the compress from the spring, how much it is compressed, that is 180 millimeters huge, 18 centimeters got compressed because of that weight. The weight is also huge amount, that is 3000 newtons, that is almost 300 kgs. 300 kgs weight when acts falls. What is that height? Such a way that the deflection becomes 180 millimeters. And the diameter of the wire, the mean diameter of the coil, that is 200 millimeters, that is 20 centimeter. And the diameter of wire is 30 millimeters. So we have to see, let us find out the height, dropping height through which the weight was dropped. Now we know the deflection 64 times. What is the weight? We have to find out. There is the weight was dropped, that weight is different, causes the work done. The axial weight caused by here, the W, delta equal to 64 times W R cube N by CD power 4. Here delta is 180 64 times WR, that is the mean radius, that is 100 millimeters cubic N, 16 by C, 8 into 10 power 4. What is the D? Diameter of the wire is 30 millimeters, 30 power 4. Then W equal to, W here, axial load acted on that equal to 11390 newtons, W, 11390 newtons. Now, what is the work done by the falling weight on the spring? The work done by the falling weight on the spring equal to weight falling times H plus delta. What is the falling weight here? The falling weight is 3000 newtons was given times H plus delta, 180 newton per millimeter. Now here, the energy stored in the spring, that equal to half load times deflection. Half of what is the weight times deflection, that weight is 11390, which is calculated, times deflection 180, that is 1025100 newton millimeter. So work done by falling weight equal to energy stored in the spring. If we equate here, then we'll get it what is the height with which the weight fallen on that. So here, why here work done by the spring falling weight is 3000 newtons, 3000 times H plus 180 equal to 1025100. What is the H value? Value of the H is 161.7 millimeter. 161.7 millimeter. That means 16.17 centimeters. 16.17 centimeters. If fall the weight, falls, the weight falling is 3000 newtons, weight falls on the spring, then the deflection comes as there is 18 centimeters, that is 180 millimeters comes. Alright. So this is the dropping weight. So this is the dropping weight with which the spring has fallen. Alright. This is the dropping weight, that is 16.17 centimeters. So thank you for this session. We have covered all types of problems in a model point of view, and in this session we have calculated what is the dropping height, what is the deflection, what is the shear stress, what are the number of coils of the closely coiled helical spring are calculated. Once again, thank you all of you.
Like, share and subscribe. Hit the bell icon for more updates.